5.3, angle bisector and incenter. The first thing is angle bisector is a ray that divides it in half. So if this is an angle, this ray, A, B, C, D, the ray BD bisects it if you see this arc and this arc. Okay, sometimes they do double arcs, sometimes triple arcs. But if you see that, then you know that BD intersects it. Or excuse me, bisects it. Okay? An example problem would be 2x and 60. Right? You would set those equal and get x equals 30. Okay? Angle bisector. Very self-explanatory, very straightforward. Okay? If I asked you to draw angle bisector, most of you probably could have drawn it when you walked in here. Alright? The next sentence says the point of concurrency. Remember, that's generic. Point of concurrency deals with all four of them. We've only learned one. We're fixing to learn number two. The point of concurrency of the three angle bisectors is called the incenter. Alright, here's my attempt at drawing. You would cut this angle in half. That's what that means. You would cut this angle here in half. And that's how that would look. How many more do we have? One. We got one more. There are a total of 3 angle bisectors in any triangle. We would cut this angle here. We would need 3 arcs to designate that that angle is congruent to that angle. And this point, the point of concurrency, when I draw the 3 ABI, that's how we remember it, ABI. When I draw the 3 angle bisectors, then this is the incenter. The incenter. The incenter, I'll go ahead and cover it, has 2 special properties. What is one of its special properties? The incenter is always what?
On the inside.
On the inside. Always on the inside. And in just a minute, I'll show you the website and I'll manipulate it and you'll see that it's always on the inside. That no matter what you do, it's always on the inside. The other special property of the incenter is that it is equidistant to the 3 what?
Angles. Sides. Oh.
Sides. Circumcenter is angles. So it's equidistant to the 3 sides. I'm doing this in red so that you can see it. That would mean that this distance here is a right angle. It has to be a right angle. This distance here with a right angle, the distances in red are the same. And this distance here with a right angle. The reason I did it in red is I want you to see that it's not a continuation of this line. This line and the red line are 2 different lines. This is the angle bisector. This is the shortest distance between the incenter and the side. That's why I did it in red. Okay? Equidistant to the 3 sides. Equidistant to the 3 sides. Always on the inside. The incenter is always on the inside. Is that easy to remember? I hope so. I hope that that's easy to remember. Alright, we've got 3 theorems here. Let's see if we've talked about them. If a point is on the bisector of an angle, then it is equidistant from the 2 sides of a triangle. We haven't talked about that yet. I'm going to erase this. Everybody got this? Still working? James, you got it? Okay. Quiet, please. All right, let's talk about theorem 5.5 here. The first theorem on page 272. If I have an angle and I bisect it with a ray. Colin, you writing this down? You got this drawn in your notes? No. The theorem says, if a point is on the bisector, any point, right? How many points are on the bisector? Infinitely many. Okay? If I just pick a point, then this theorem says that it is equidistant from the 2 sides of the angle. That means that this distance has to be the same as this distance. That distance has to be the same as that distance, even though it doesn't exactly look like it on my hand drawing up here. If this was an angle bisector, then that distance and that distance would have to be the same. Now, what two things do you see there? You see the box. What does that represent? 90 degrees. Remember, the shortest distance between a point and a line is always perpendicular. So that has to be a right angle. That has to be a right angle. If you see the both boxes and you see the slashes, that slash and that slash, then you can say, yes, it is on the angle bisector. That's theorem 5.6. Okay? Let's talk about that. It's backwards. It's the converse. Let's read it again. If a point is on the interior of an angle and it's equidistant, then what must be true? Then AB has to be the angle bisector. Get it? AB? Angle bisector?
I get it.
If you know this and this, then you can say this, that AB is the angle bisector. They go hand in hand. If it's on the angle bisector, then you know it's equidistant. If it's equidistant, then you know it's on the angle bisector. They go hand in hand, 5.5, 5.6. Okay? We'll do some examples in your workbook in just a minute, and I think that'll make a little bit more sense. What two things? To hit on it again, what two things must you see?
The box.
You must see the box, and what else?
The dash.
You must see the slash. Let's look at a counter example. A counter example to that would be this. First of all, is that the angle bisector? No, it doesn't look like it. Could both of those distances be 8?
No.
Yeah.
Yes.
They could be. Right? They're the same length. 8 equals 8. But is AC, is AC the angle bisector in this case? No, why not? Because you don't see the what? You don't see the box. So it would say, is AC the angle bisector? And your answer would be no. Why not? Because you don't see the boxes. Okay? How about this one? Is AC the angle bisector now?
No.
Why not?
Because you don't see it.
You got the boxes, but what do you not know? You don't know the slash. This could be 7 and this be 5. They're not equal. If you don't see that it's 7 and box, then you don't know. So this would be no and this would be no. Okay, you want to see an example of yes?
Yeah.
What if you just have one box?
How about now?
No.
Is that an example of yes or no?
Yeah.
Is
Yeah.
AC the angle bisector?
Yes.
Only one box. You got to have boxes on
You gotta
both.
have both boxes.
Both of them have to be your right angle. Now is it yes? Now AC is the angle bisector. Questions? Any questions? All right, the last theorem we've already talked about. Read it out for me, Emilio. Nice and loud. Theorem 5.7. It's up there on the smart board.
The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle.
What's the most important word in that theorem, Emilio? A couple of them, but what's the most important word?
Intersect
They intersect at a point
at a point that's equidistant
from the sides. I would say that sides is the most important word in that theorem. Because when we talked about circumcenter, what was it equidistant to? The angles. So circumcenter is equidistant to the 3 vertices or angles. Incenter is equidistant to the 3 sides. You better circle sides in your notes right there. Circle it, highlight it, star it. The incenter is equidistant to the 3 sides. Okay? Very, very important. We're going to do an example here in just a minute. All right, everybody get your workbook out. And let's practice some problems out of our workbook. We're doing good on time.